Okay, welcome back. So now we are switching gear to the general circuit model. So what Ibrahim talked about is the quantum annealing. Now we going to talk about the quantum circuit model and some of its applications to the spatial data. So as we said, quantum computing is a field at the intersection of computer science, physics, and mathematics, and it leverages some phenomena from quantum physics like superposition, interference, and entanglement to design efficient algorithms that can solve some of the problems in a much more efficient way compared to their classical counterparts. So actually in this part of the workshop, we are going to show you some examples of these algorithms. So I'll give you more detailed background. Then we'll give some quantum algorithms examples in general, famous ones like quantum teleportation and so on. And finally, I'll show you some of the examples of our research in applying quantum computing for positioning and navigation applications, which is one of my main areas of research. And we conclude and give some directions for future work. So as we said, the basic unit of computation in a quantum computer is the qubit. And the qubit can be in a superposition of 0 and 1 at the same time. How do we physically implement? I think that was Maria's question. She needs some intuition about the physical implementation. Typically, qubits are implemented by some features of elementary particles. So the state of the qubit can be the state, for example, of the polarization of a photon or the spin of the electron. So you can take these features and map them to qubits. Of course, in computer science, we make an abstraction, so we don't care about the physical implementation. We abstract this. So mathematically, the way we write it is, this is the state of the qubit, if psi is equal to a superposition of the 0 and 1 states. And this superposition is alpha 0 plus beta 1. And the condition here is alpha squared plus beta squared must add up to 1. Why it's alpha squared plus beta squared add up to 1, not alpha plus beta? Because actually alpha and beta in general are complex numbers. So since they are complex number, their amplitude squared is actually, this is the probability of the mix. So alpha squared is the probability of being in state 0, and the beta squared is the probability of being in state 1. And by changing alpha and the beta, you are changing the amount of the mix, or the superposition amount, and that's why they had to add up to 1, because this is a probability distribution. Why actually we need complex numbers, not real numbers? Because actually using complex numbers allows you to have a phase. So you can do constructive and destructive interference. And actually this constructive and destructive interference is what we leverage in our algorithms to achieve what we want. I'll talk about this in more details later. So as we said, when I measure, what will happen? When I measure a qubit, what will happen? So it's in a superposition in a mix of 0 and 1. Then I measure this qubit, I will get a classical 0 or and 1. Based on what? Based probabilistic, based on actually alpha and beta. So I'll get 0 with probability alpha squared, and I will get 1 with probability beta squared. And as we said, this is destructive, meaning once I get 0 and 1, I cannot go back to the superposition again. So once I measure, I lost my superposition and I cannot go back again. So the qubit is the data, our unit of computation. And of course, if you have multiple qubits, so here we have 4 qubits, you can have all the possible states, combination of these 4 qubits. So you can have from 4 zeros until 4 ones. So actually, as you increase the number of qubits, the number of states you have is growing exponentially in the number of qubits. And as I said, when you perform operations, you are performing operations, if it's a single qubit, you are performing on 0 and 1 at the same time. If you have 4 qubits, you have 16 possible combinations, and you are working on the 16 possible combinations in parallel. And this is what gives you the quantum parallelism and the quantum advantage. How do we process? So qubit is the data. How do we work on the data? We use quantum circuits or quantum gates. So you write your algorithm as quantum circuit. So quantum circuit is similar to classical circuits. You have gates like AND, OR, XOR, and so on. But actually, these gates works in qubits instead of working on classical bits. Some of the famous gates are the NOT gate, Hadamard gate. They work on a single qubit. I'll give you more details later about them. But actually, you can have 2 qubit gates, 3 qubit gates, and so on. I'll give you examples on those. What do the gates do? So you enter with a certain state of the qubit, and you exit with another state. What does this mean? You enter with a certain alpha and beta, a mix of 0 and 1, and you exit with a different mix. And if you think about it, actually what they are doing is they are interfering with the state of the qubit. So they are changing it. So this is what we call interference. So the gate, what they are doing, they are interfering with the state of the qubit, and by doing this, they are changing it to a different state. Let's take some examples. So the simple one is the NOT gate, or the Boole X gate. So what it does, it's a NOT gate. So what does a NOT gate does in classical computing? It inverts 0 to 1 and 1 to 0. So actually this does exactly the same, but the main difference is instead of working in classical bits, it works in qubits. So the input can be a general qubit in an arbitrary superposition. And what it does, so if your input is alpha 0 plus beta 1, the output, you will invert these. So the output will be alpha 1 plus beta 0. And you inverted 0 and 1 at the same time in one operation. Any problem? So this is one of the famous single qubit gates. Another one is the Hadamard gate. What the Hadamard gate does is it takes a pure 0, meaning it takes a qubit in 100% 0, which is a special case of the mix, and it put it in an equal superposition of 0 and 1. Why 1 over square root of 2? Why not 1 over 2? Any hints? Yes, because we said the probability is the square. We call actually these probability amplitudes. They are not probabilities. Because as we said in general, they can be complex numbers. Their amplitude square is the probability. So actually that's why the amplitude square of this is 1/2. So this is the probability of getting 0 and 1. So if you have 0, you will get equal superposition of 0 and 1 with the plus sign. If you have 1 instead of 0 in the input, you get still an equal superposition, but with a negative sign. Is negative sign okay? Yes, because we said in general, the amplitude, probability amplitudes can be complex numbers in general. So actually, you can even have complex numbers here. So these are examples of single qubit gates. We can also have more than one qubit gate. So this is a qubit circuit gate that takes 2 inputs. And actually, this is C0. What is C0? It's a controlled NOT gate. So actually, you have 2 qubits in the input, and you get 2 qubits in the output. And what it does is, when the control is 1, it performs the NOT operation on the second qubit. When the control is 0, the NOT operation is not performed, and it's just passed through. What is in the input goes to the output. So in this particular example, the control is 1, meaning the NOT gate is enabled. So what will happen? It will invert the 0, and that's why we got 1 and 1. Anyone doesn't understand why we got 1 and 1 for the input 1 and 0? Yes, good question. So actually here I'm showing to you 1, 0 and 1, 1. But actually this is a quantum gate. What does it mean? It means that the qubits here can be arbitrary superposition of 0 and 1. So your control can be an arbitrary mix of 0 and 1, and your target can be an arbitrary mix of 0 and 1. So actually what happens, your control is probabilistic, and your target is probabilistic. So what mix do I get? We'll talk about this example later. But one important thing to remember here is that the mathematical theory that models this is again linear algebra. So it's a linear system, which means you can do superposition. So if I have an arbitrary mix, I can break it into its components and then do a superposition in the output. Great questions. Other questions? So C0 is an example of 2 qubit gate. An example of 3 qubit gate is the C swap gate. And as the name implies, it's a controlled swap. So you have a controlled qubit. When it's 1, you perform the swap operation. When it's 0, you don't perform the swap operation, and the input passes as is to the output. So in this particular case, the control is 1. So the swap is enabled, and your input is psi and phi. That's why the output is swapped. You get phi and psi. And of course, the order matters. Any questions? Great. So these are examples on quantum gates. How do I write my quantum algorithm? I write it as a quantum circuit. It's a collection of quantum gates. So this is a very simple example of a quantum circuit. So what I do here, I start with pure zero, meaning 100% 0 and 0, 1. I pass it by the Hadamard gate. What would be the output here? 0, I pass it by Hadamard. What do I get in the output? Yes, thank you. It's a 50%, 0 and 1. And that's why when I measure, I'll get 0 and 1 with equal probability. One thing for the notation here is single lines represent qubits, meaning you can have superposition, but double lines represent the classical bits. And usually you get classical bits after you measure, because as we said, when you measure, it collapses to classical bits. One very interesting thing to notice here is when I'm designing a quantum algorithm, how do I design it? I put an input, and then I want some desired output. So if you think about, for example, integer factoring, what do I want? I want in the input to put the number I want to factor. And I want in the output to get the factors of this number. So if I put 15, I want to get 5, for example, in the output. But as we noticed, this is probabilistic. The output I get is probabilistic. How would I get it? So actually, I want to select my gates, which is my algorithm, that regardless of the input I put, I always get the correct factor. Got it? So my algorithm, the gates don't change. So I want to select some gates that don't change. But regardless of the input I put, I always get the correct output. How would I do this? We said gates do interference. So you are changing, you enter with a certain input, your gates will change the probability of the different possible outputs. But when you how do I get my output? At the end, I need to measure to get an answer. But when I measure, what do I get? Can't hear you measure. It's probabilistic, so I'll get a random answer. But actually, I don't want to get a random answer. I want to get the correct answer. If I give you 15, I want to get 5, not just any random number. So how do I do this? Actually, by choosing the gates. Because the gates will change, will do interference, and they change the probability of the different possible answers. But my goal as a quantum computing designer, algorithm designer, is to select the gates. And these gates are constant. They don't change based on the input. That whenever I give you any number, you increase the probability of the correct answer. So that when I measure, I get the correct answer with high probability. And when you think about it, this is not trivial. Because as we said, the gates are independent of the input. So I need to select a subset of gates that always give me the correct answer, regardless of the input. Got it? And that's why it's an interesting way to look into the problems. So what we'll do in the next part of the talk, I'll give you some examples of famous quantum algorithms. So the first one is trivial, actually we already covered it. It's a true random number generator. Then the second one is the Bell's circuit. I'll tell you what it does. And finally, we'll use Bell's circuit to implement the famous quantum teleportation algorithm. We'll teleport qubits. So actually, what do we mean by true random number generators? As we know, in any programming language, I have a function that I ask it to give me a random number. But actually, those are the random numbers I get from the rand function in C, for example. Is it truly random? Of course not. Why? Because it's a function. So it's an algorithm that generates this number. So actually, the numbers coming out from the rand function, they are pseudo-random because they look like random numbers, but actually they are generated by an algorithm, which means they are not random. But actually, the random numbers we get from a quantum computer are truly random, meaning the probability of getting 0 and 1 are truly random. So if you want to generate true random numbers, actually the circuit I just showed generates true random numbers with equal probability. 50-50. So just you start with pure 0, pass it by a Hadamard gate. The output here will be an equal superposition of 0 and 1. So when I measure, I get 0 and 1, and this 0 and 1 are true random number with equal probability. Any questions? Good. Let's take more interesting examples. So here we'll talk about Bell's circuit. So what is a Bell's circuit? This is actually the Bell's circuit, and whenever you can think about it, this is a quantum computing algorithm because it's a collection of gates. And I want to know, what does this circuit do? What does this algorithm do? So what we do is we have 2 qubits. So I need to try the 4 different bases, the 0, 0, 0, 1, 1, 0, and 1, 1. And why is that? Because we said the mathematics behind it is linear algebra. So it's a linear system. So if I know the output for each elementary state, I can just do superposition for any arbitrary combination, and I can get the output. So my question to you is, what happens if I put 0, 0 here? What would be the output? And the way we do it is we trace the circuit level by level. So I start here, I have 0 and 0. What would be the output after the Hadamard gate? Any guesses? So the first qubit, Rolla? Yaron, sorry? Yes. So this one will give me 0 and 1 with equal probability, and the other one I didn't operate on it, so it will pass as is. Any problem? So when I apply Hadamard to the pure 0 state here, I will get 0 and 1 with equal probability, and the other is not changed. So the combined system state at this point after the Hadamard gate, this is the first qubit, and this is the second qubit. I can distribute it. It's a linear system. So I can be either in state 0, 0, the 2 qubit, or state 1, 0 with equal probability. Any problem? Good. Then the next step is to apply this C0 gate. So this is the input to the C0 gate. What would be the output? So again, it's a linear system, meaning I can be in this state or this state. So I can apply the gate to this input and apply it to this input and then combine them to get the output because of the superposition linear property. Question, please. This one? I have 2 zeros. Yes, so I have 2 qubits because I have 2 lines. Each line represents a qubit. And they are pure 0. I started with pure 0, 0. No, actually each line is a single qubit. Good point. So if I have 0, 0, the first one will be changed to equal superposition. Second one will remain 0 because I didn't operate on it. And then since it's linear, I can distribute. So this is the joint system state. I can be either in state 0, 0 or in state 1, 0 with equal probability. Then I want to apply C0 to this combined state. How do I apply it? I leverage the linear property. So I apply it to each input and then combine it in the output. So when I apply to 0, 0, what will happen? It's a controlled NOT. How does the controlled NOT gate work? If the control is 0, you don't do anything. If the control is 1, you perform the NOT operation. Here the control is 0. So you don't do anything. So actually the 0 will pass as is. That's why 0, 0 will give me 0, 0. But the second state, the control is 1. What will happen? So the control is enabled. It will perform the NOT in the second qubit. So this 0 will change to 1. So this is the state immediately after the C0. Any problem? So actually this is a circuit or algorithm. When I give it 0, 0 in the input, which is a pure 0, 0, it will give me in the output an equal superposition of 0, 0 and 1, 1. Anyone don't see why this is the case? Good. So this is if the input is 0, 0. What about if the input is 0, 1, 1, 0, 1, 1? It's a good exercise to do it at home or at your hotel room. But this is the 4 different combination. When I apply the Bell circuit to 0, 0, this is what we did. But when I apply to 0, 1, I get a different state. 1, 0, I get a different state, and so on. And you can see why this is negative and this is positive. Any idea why this is positive and this is negative? Sorry? Yes, because we said Hadamard, when the input is 1, it gives you a negative sign. That's just to give you a hint why you have 0 minus here and the positive here. Please.
So the two outputs have the same value. You have two input and output, right? And it kind of gives the same output.
So actually, this is an entangled state. Entangled meaning they are correlated. Again, you can think about like a joint distribution. So actually, let's think about it. What will happen when I measure these 2 qubits at the output? Any idea what will I get? Yes, it's a probabilistic. So what will I get? So we have 4 different combinations. I'm measuring 2 qubits. So I get 2 classical bits. So I can get 0, 0, 0, 1, 1, 0, and 1, 1. So the question is, with what probabilities? Anyone can guess? With what probability will I get 0, 0, for example? 1/2. Why? It's correct. Yes, exactly. Because actually we said this is the probability amplitude. And the probability is the square of it. Thank you so much. So actually I'll get 0, 0 with probability half. And I'll get 1, 1 with probability half. What about 1, 0? I can't get it with probability 0. What about 0, 1? I cannot get it. Here, it's the same thing. I get 0, 1 with probability half and so on. What if I measure only 1 qubit instead of measuring 2? So what if I measure this qubit only? What will happen? How many classical bits I will get? I measure just 1. Exactly. And that's why they are entangled. So actually I measured 1 qubit, I should get 1 classical bit. So if I measure this, actually again, it's a joint and marginal distribution. It's the same idea. So if this is your joint distribution, 0, 0 is probability half, and 1, 1 is probability half. If you measure just the first bit, or the first qubit, you will get 0 with probability half, and 1 with probability half. But if I get 0 here, what would be the state of the second qubit? It must be 0, because I don't have a state 0, 1. So if this turns to be 0, the other one must be 0. And if this turns to be 1, the other one must be 1. And actually, this is the entanglement. They are highly correlated. Even if one of them is here and the other is on Mars. If I measure and I get 0, for sure I know the other one must be 0. And again, this is what Einstein didn't like. That I'm doing something here and it's affecting something that is not in a locality. Got it?
If you don't measure the one,
if I don't measure, they are still in the joint state.
no, but when you measure one on the earth, one of them will become 0 immediately.
Yes, 0 time. 0 time. You know for sure. It's just from the probability. And it's spooky. What's going on? Which is very interesting. Any questions about the Bell circuit and what it does? Good. Actually, the next step, we'll use the Bell circuit to do quantum teleportation. Before this, there is the reverse Bell circuit. What is the reverse Bell circuit? It's actually in quantum computing, all gates are reversible. What does this mean? That if I give you the output, you can always find the input. Is this true for classical gates? No. Why? For example, the AND gate. Is the AND gate reversible? If I give you any output, can you know the input? If the output is 1, what would be the input for the AND gate? 1, 1. But if the output is 0, it can be 0, 0, 1, 0, or 1, 1. So it is not reversible. But by definition, all quantum gates are reversible. All quantum gates. So if I give you any circuit, you can find its reverse. Actually, how do we present the gates mathematically? They are matrices. And since they are matrices, actually they have to be unitary matrices, which means you can always find the inverse. And actually this inverse is the reverse gate for it. So anyway, what is the reverse Bell circuit? is actually this circuit. The Bell circuit was Hadamard followed by C naught. Its reverse is C naught followed by Hadamard, which means if I put 0, 0 here and I pass it by this circuit, I will get 0, 0, same input. And if I put 1, 0, I'll get 1, 0 because I'm reversing the circuit. So it's like identity. I'm getting identity. Any problem? So the reverse circuit of the Bell circuit of 0, 0, 1, 1 will give me 0, 0. And the other states will give me the elementary states I started with. Any problems? Mishal?
So from the top diagram, so if I always have the circuit and then followed by a keyboard, I go back to whatever I started from.
Exactly. You get the same input. You reverse the circuit, which means it's identity. So you always get the input. Great. So moving to the famous quantum teleportation algorithm. So this is quantum teleportation. You know Star Trek, where they teleported some of the crew from Earth or from the planet to the ship. So actually we are doing this here, but actually we are not teleporting objects or humans. We are teleporting qubits. We'll see what this means in the next few slides. We'll come to this. So actually, what is the problem definition? We have Alice and Bob. We want to teleport a qubit from Alice to Bob. So Alice has a qubit in a general state, alpha 0 plus beta 1. This is a general qubit in any state. And it wants to have Bob receive the qubit in the same state. How would it do it? It will do it by sending 2 classical bits. So I am Alice here in this room, and the Bob is on Mars, and I want to send to Bob a qubit in any arbitrary state. To do this, I'll send Bob 2 classical bits. And the Bob, when he receives these 2 classical bits, will automatically have the qubit state that Alice has. Anyone find something strange here? Or doesn't make sense or interesting or Amr? Close enough. So actually, we said how many possible states I can have for a general qubit? Infinite. So actually, I want to tell Bob one out of these infinite states by sending them 2 bits. So how can I just using 2 bits determine one out of infinity? This is weird, right? So actually, there is a trick. The trick exactly. So actually, the trick here is that they already have entangled the qubits beforehand. So they have this entangled the qubit, then they will receive 2 classical bits Bob, and by doing this, Alice can transport this state to him. We'll see the details, but again, this is the main idea. So as we said, and as Yaron mentioned, they will start with 2 qubits that are in this entangled state. How can I come up with this entangled state? Using the Bell circuit that we just talked about. So I start with 2 pure zeros and then pass them by the Bell circuit. I'll get this entangled state. We do this in the lab before Bob leaves, and then I keep one of them with me, Alice, and Bob takes the other and travel to Mars. But I know they are in this particular state. And I prepared this when they were together before he left. Then Alice has a new qubit. This is different from these 2 qubits. So in total, we have 3 qubits. And she wants to transfer this state to Bob using the entangled qubits that they shared before, and by sending 2 extra classical bits. So how can I write my algorithm? It's a collection of gates. How many qubits I have in total? 3, thank you. The 2 that we started with entangled, plus the one I want to teleport. Okay? Let's look at the algorithm, which is the circuit. So I have 3 qubits in total. These are the 2 I started with in the entangled Bell state. So I started with this, and this is the qubit that Alice wants to teleport. So even though Alice and Bob can be at different locations, when I write the algorithm, I'm writing them in the same circuit because of this entanglement thing. When I do something on one of them, it affects the other, so I can write them in the same circuit. Okay? So does this do teleportation? How would I know? I do exactly what we did before. I start from the input and then trace it level by level to see what the output will be. So what is the joint state in the input? What is the system state? In the input, I have 3 qubits. So what are the possible combinations? 0, 0, 0, 0, 0, 1 until 1, 1, 1. But of course, what matters is what is the probability amplitude of each one of these states. So how do I get it? It's just like the joint probability between these two. If the first can be in state A0 plus beta 1 and the second can be in this state, I can do the distribution because we said it's a linear system. So the joint state is 0, 0, 0 with probability amplitude A over square root of 2. Or 0, 1, 1 with probability A over square root of 2. Or 1, 0, 0 with B over square root of 2. Or 1, 1, 1 with B over square root of 2. I cannot have, for example, any other state that is not in these 4 combinations. It's impossible. Any problem? And of course, if you do mathematically, it makes sense that the summation of these add up to 1 because it's a probability distribution. It's exactly like marginal and the joint distributions. Same concept. Good? So as we said, the initial joint state is I take this and distribute it over this. So this is the 4 different states I can have. What do we do next? I apply a C-NOT gate. The C-NOT gate works on the first 2 qubits. So what I do, I just rearrange the terms. I separate the first 2 because these are the 2 I'm going to operate on. The third is not going to be affected. Any problem? So I take just the first 2 qubits. And then, since it's a linear system, I can apply the C-NOT gate to each one of these and then combine the outputs using the superposition property. So when I apply C-NOT to 0, 0, what would be the output? The control is 0, so the NOT operation will not be performed. So I get 0, 0. If I apply 0, 1, what would be the output? Apply C-NOT to 0, 1. 0, 1, because the control is 0, it will not be inverted. When I apply C-NOT to 1, 0, what do I get? 1, 1, because the control is 1, so this would be inverted. When I apply it to 1, 1, I get 1, 0, because the 1 is enabled, so 1 will be inverted to 0. So actually, if this is the input, the output would be the same, but as we said, this would be 1, 1, and this would be 1, 0. Any problem? So actually, this is the state, the joint system state after the C-NOT. What do I do next? Apply the second level. So I apply the Hadamard. Hadamard is applied to which qubit? Only the first. So I just take the first out because I'm going to operate on it. And the remaining, of course, the order matters because this is first, second, third qubit. So I just separate the first qubit because I'm going to operate on it. And since it's a linear system, I apply it for each special case and combine the output. If I apply Hadamard to 0, what do I get? Half and half, 0 and 1 with a plus sign. When I apply it to 1, I get half and half, but with a minus sign. Got it? So actually, this is what we do next. So as we said, 0 will be mapped to equal with plus, and 1 will be mapped to equal superposition, but with a minus. So it's just I do mathematical manipulation, distribution, and then I collect the similar terms. So actually, this is what I get, and each color is the same term. So blue is exactly the same term, green is the same term, and so on. Any problem? Good. So this is the state after the Hadamard gate, the joint system state. Great. So I just rearrange, meaning I'll take similar terms together and take this as a common factor. So the green, for example, will be 0, 1 multiplied by 0, 1, and so on. So this is what I get after doing this. So this is the state at the end after rearranging. What do I have? 0, 0 multiplied by this, 0, 1 multiplied by this, and so on. What was my goal of this algorithm? Anyone remembers? Or we are lost in mathematics? What was the original goal? Teleport a qubit. Which qubit? I wanted to teleport this to Bob. So actually these, we said we started with this 2 qubit entangled in this Bell state. One was Alice on Earth and the other was Bob on Mars. And then Alice had this qubit and she wants to send it to Bob. So actually what I wanted to do is to end with Bob having this state. So I want Bob to have A0 plus B1. Got it? Bob is the third qubit. So actually where is the third qubit here? This is the out. It is this one. You can find it's very close. I wanted A0 plus B1. So I have here A0 plus B1. But here I have A1 B0. It is not the same. Got it? So what I want to do is, in all cases, I want Bob to have A0 B1. Regardless of the state. Here, if I measure, if Bob measures, actually Bob cannot measure, because if Bob measures, it will collapse to classical bit. It is not teleportation. Got it? So what will happen is Alice will measure. So Alice will measure. What will Alice get? Any idea? Where are the qubits with Alice? It's the first 2 qubits. So when Alice measures, what will she get? She will get one of these 4 states with what probability? With this square. So it will get 0, 0 with probability 1/4, 0, 1 with probability 1/4, and so on. So it will get a random 2 bits, classical bits, right? If Alice gets 0, 0, what does this mean? Why? Because actually if Alice gets 0, 0, I must be in this situation, because this is a joint system state. So if Alice gets 0, 0, for sure Bob will have A0, B1. And this is a desired thing. What if Alice got 0, 1 instead? How can I switch this to A0 plus B1? I apply C naught. Actually, C naught or just not? Just not gate. It is not conditioned. I apply the not gate. What if Alice gets 1, 0? It is not, but with a negative sign. Actually, there is a gate that does that, the Z gate. It's a different gate. What if it gets A1 minus B0? So actually, this is Z and not. Because you need to flip the sign and flip the bits. So actually, the algorithm is Alice measures. So you'll get one of these different 4 combinations at random. But what she will do is she will send these, what she gets, to Bob. These are the classical bits. I want to send 2 classical bits. The 2 classical bits you will send is what Alice gets. It's random. But by sending them to Bob, Bob knows how to correct its qubit state to match for sure the original qubit that I wanted to teleport. Wow, this is nice, right? So this is actually quantum teleportation. So actually, physically, the qubit wasn't teleported. Actually, what happened is the state of this qubit changed it to the required state, and actually Alice lost these 2 qubits because when she measures, they are classical qubits. But I can use it to send qubits from one location to the other. And actually, quantum teleportation is the main algorithm behind quantum communication. So when you want to send the qubits from one device to the other, you usually use quantum teleportation. Because you are moving the data from one, you can think about Alice as one machine and the Bob is another machine. Got it? This is important. Why? Because actually there is a theory in quantum computing called the no cloning theory. What does this mean? No cloning theory means you cannot clone a qubit. If I have a qubit, I cannot take a copy from it. Can we take copies in classical computing? We do it all the time. So x equal y. This is a copy in programming. In the lab, when we have wires coming out from one variable and we are distributing it, this is copies. In quantum computing, you can prove you cannot do this. The proof is easy. Simply, it's by contradiction. You say there exists a cloning circuit, and by contradiction, you show you cannot have this circuit. So you cannot clone a qubit. This has implications. So actually, if I cannot clone, how can I communicate? Because when communication, usually you buffer, you send it to the memory buffer, and then the operating system buffer, and you send it. I cannot clone. So actually, that's why you use teleportation. The other application, of course, is in security. Because in security, imagine the attacker cannot buffer the data because he cannot clone it. So the only things he can do is to measure when the data is in transit. And what happens when the attacker measures? Measurement is destructive. So they will affect the data in transit. So the legitimate nodes can at least know that someone is spying on their data. In classical, you cannot do this. But in quantum, because of the no cloning theory, it has an advantage where you can know that there is an attacker in the middle.
So if like Bob now knows which of the cases it is, he'll just apply the right gate.
Exactly. So actually, this is in the next slide. So if Alice have 0, 0, you have this. If you have 0, 1, you have this, and that's why you need to send 2 classical bits so that Bob knows what Alice, and by knowing this, since they are entangled, you know which state, and you can easily correct it by applying the gates. So actually, this is what you are seeing here. If you get 0, 0, do nothing. You know it's in the correct state. If you get 0, 1, apply the NOT gate. If you get this, Z is the phase change. It switches from positive to negative. 1, 1. Actually, Y is a combination of X followed by Z. And actually, we said each one of these is a matrix. So basically, it's 2 matrix multiplication. You get the Y gate. Yes, please.
Is it the case that you never apply something because probability communication works is 25%, and you rely on the case you don't do something?
So here, of course, is theory. So you assume everything.
Yeah, but in the end, you just wait for the and add it. I mean, you do this over and over again, and then 25% of the cases you observe, you add it. And this is the only case you actually need to handle in order to communication.
You do this, but actually the problem here is whenever you measure, so in order to get 0, 0, you measure. You distracted a pair of entangled qubits. So usually if you order, the way I imagine it, typically how it would work is before you travel, you have 1,000 qubits, for example. So this is your budget. I can teleport 1,000 qubits.
But it depends. For satellite, for example, you use laser. I mean,
but laser, you need line of sight. So again, yeah. But I got your point. But again, it's mainly a theoretical exercise. Of course, we have also error correction algorithms. So if you have errors, quantum error correction algorithms. What is the problem with quantum error correction algorithms? Usually you depend on redundancy. The famous one is just if you, instead of sending 1 0, send 3 zeros and then do a majority vote. But in order to send 3 zeros, I need to clone. And we said I cannot clone. So how can I do error correction when I cannot do cloning? Very nice ideas in quantum computing algorithms in order to do all of these. But I hope that I just enticed you to see how this fascinating world works. Great questions. Any other questions or comments? Mishan, please.
So I think it's important, like the definition of the entanglement of part of the data already Bob.
Yes.
Again, maybe
And this is what allows you to send infinite number of combination. You cannot just send 2 classical bits and get infinite number of states.
right. That does I mean like not send some unknown like destination. It has to be somewhere that
Yes, you have to be entangled, and you can think about it. It's like, as I said,
like,
it's
I'm thinking like no, like I'm thinking data. Maybe like, I know there are like some differences between whatever we are.
but actually this is quantum communication where you have quantum routers, and then you have connection. So the router and your neighboring router, you have these entangled qubits. But this router and the next router have their own entangled qubits. And then you can do this routing.
But it's like figure out like known to each other.
Yes, exactly. They have to be in advance in order to do this quantum teleportation. And actually, in reality, in the news, actually, as I showed in the beginning, they said Chinese scientists, for example, teleported a qubit from Earth to a Chinese satellite in space. So actually, this has been implemented in practical situations. Great questions. Other questions? So before, another thing, of course, is we are back again to supernomial communication. So we said the state at Bob, when you measure, Alice measures 0, 0, jumps in 0 time. Does this imply that you get infinite speed, meaning faster than supernomial communication? No, and the short answer, why? Because actually Bob has to wait for the 2 classical bits to arrive in order to convey the information. And in order to send these classical bits, you will need to send them with less than the speed of light. So it's the same thing. So teleportation doesn't allow supernomial communication. Any questions? Yeah.
Actually, when you're transporting, you're sending in some way 3 different values, right? X, the Y, and the Z. Is there a way? I know that in compression sometimes they separate between the X, the Y, and the Z. Is it possible also to do something like that in teleportation, so you only send south state, maybe reduce your budget by that?
Good question. The short answer, I don't know. And of course, there is quantum computing is a new computing paradigm. So actually, you have quantum computational classes. So you have complexity classes for quantum computing. And I think I think your question is this the best you can do? So I think one of the research in this area is actually quantum teleportation the optimal. But since it's famous, I imagine without proof that this is the best you can do. I think you cannot do better than this under some assumptions, of course. But this is a great question to explore here. So in the remaining 10 minutes, maybe we can show this in action. So you have many simulators, of course, and you can deploy this. So actually, IBM Qiskit have free accounts for researchers where you can access a cloud quantum computer for free. I think D-Wave also have this possibility, but maybe you need to sign up for this. But you have many simulators. And in the small cases, you can do this. I can show you actually this simulator, but I'm showing you the algorithm. So as we said, I need 3 qubits. Alice has 2 of them. Initially, the one that was entangled was Bob. So I start with 0, 0, but I need to reach the Bell state. That's why I have the Bell circuit that we talked about before. And the output here is the entangled state that we saw, 1 over square root of 2, 0, 0, plus 1 over square root of 2, 1, 1. So I had to do it myself because I'm starting from 0, 0. And then actually this is what we did in quantum teleportation. Actually, what is this circuit? Anyone? So quantum teleportation is based on what? Yes, exactly. So this is a quantum teleportation algorithm. It is the reverse Bell circuit. But actually, I'm not applying it to this. If I apply to these 2 lines, I will get 0, 0. That's why the devil in the details. I applying it to another set of qubits, and that's why I get the interesting interaction between the different qubits. So simply, this is the reverse Bell circuit. And then I measure. In my simulator, this is the icon, and that's why I get classical bits. I send them to Bob, and actually what Bob does is, this is how I write my algorithm. So actually this is controlled the gates, but it's controlled on the classical bits. So if I get 0, 0, what will happen? It's a control gate. When the control is 0, nothing happened. And actually this is what I wanted to do. When it was 0, 0, I already have the correct state. And then what happened if I get 1, 0? It means just apply the NOT gate and don't apply anything. So actually, just in this, I can do the 4 different combination as part of my algorithm, which is interesting. Let's see how to do it in the simulator. Do we have time? I think, yeah, we can do it. Our boss, can I show it in the simulator? Okay. Not yet. So actually, this is one of the lightweight, easy simulator I like. It's called the Quirk. So if you Google Quirk Quantum, just to give you a link, it's an online website for simulating. And actually, what you can see is just drag and drop. So you have, these are 2 qubits. What I can do is I can start, these are the gates. So this is the NOT gate, this is the Hadamard gate, and so on. So as we said, we have 3 qubits. So the way you do it is, and I apply the Bell circuit. So the Bell circuit is the Hadamard followed by C NOT gate. And in order to, this is the control, as you can see. So if I put it on the line, it will automatically connect. So this is a NOT gate. When I put it here, I converted it to a C NOT gate just by drag and drop. So this is Hadamard, and this is followed by the C NOT. So this is the Bell state. So after here, it should be in the 1 over square root of 200 plus 1 over square root of 211. And actually, this is visualization. So I can see here, this state of the qubit is 50% 1. So it can be 0 or 1. Better? Yes, for this certain qubit. So it's just on one line. So this is a probability of 1 qubit. This one is the overall system state. And this particular state, you can have, it's 1, 1 and 0, 0. And you have 8 different states because I have 3 qubits. But not all states are valid because of this particular combination. Then what do I do next? I do the reversible circuit on the first 2 qubits. So the reversible circuit is C naught. So I put a naught and the control, and followed by the Hadamard gate. So what happened here is this is the entangled qubits. This is the reversible circuit. And then I measure. This is the measurement icon. I just drag it, and I want to measure the first 2 qubits. I just measure the first 2 qubits. And then Bob needs to apply the correction. So what is the correction? As we said, as we saw in the slides, the correction is in the 3rd qubit, but it's controlled by the 2nd. Was it Z or Y? I think Y, right? Oh, sorry, because we said Y is X followed by Z. So it would be Z. Of course, the devil in the details. If I put Y, it wouldn't work. It's a different algorithm, which is part of the fun. And of course, this has to be controlled by the 1st and 2nd. We can see. So actually, what I'm doing here, what does this algorithm do? It should teleport what? The first qubit, right? At Bob. Does it did this? Actually, if you think this is state 100% 0, that's why actually the state here is 100% 0. Got it? So actually, I teleported this 0 to here. In order to do it, what you can do is you can click on this, and by clicking, you switch between some basic states. So for example, when I click on this 0, it will convert to 1. So what I should see, I should see flip to 1 because I'm teleporting this. Got it? Let me see if it works. Yes. If I click again, it will switch it to an equal superposition of 0 and 1. It has a symbol that is plus symbol. So the plus state is the equal superposition of 0 and 1 with plus in the middle. And that's why I'm seeing here 50% because I'm teleporting the plus state. If I click again, it will be the minus, which is 50%, but with a negative phase. So I should see this 50%, but actually this is a block sphere. I should see this switch on the other side because of the phase change. Yes, it's working. Makes sense, it's fun. And this is actually very powerful because you can define your own gate. How do you define a gate? It's basically a matrix. So you define the matrix of the gate. And once you do it, it will appear here as a special gate that you can reuse. You can take part of this circuit and name it as a new gate, and so on. So actually, it's a powerful simulator, but it's a classic simulator. So it's limited in the number of qubits and so on. But actually, all the IBM Qiskit, for example, has its simulator where you design your circuit like this. You can write Python code also to write your circuit. But once you run it on the simulator, the same code, same circuit, you can run it on a real computer. So actually, you have a number, maybe 10, 15 papers now. All our results are coming from real quantum computers. They are not simulators. We are getting results from real quantum computers. Some of them, we have noise effects. So in theory, when I measure, I get 0 or 1. It doesn't. We'll see this in the next part of the talk. Let me talk about it in the next part. For now, just we have 3 minutes. Any quick questions? Which ones? This one?
Yeah, to the right. Like,
this one?
Yeah.
This is the overall system state. So I have 3 qubits. So I have in general 8 states. So these are the 8 states, and this is the probability of each one of them. If you hover over them, it will tell you, and actually it's a complex number, because we said in general they are complex numbers. So what is the probability of each one of these states? Probability amplitude, whose square is the probability. Great questions. Other questions? Very good. Thank you all. It's time for our keynote. Looking forward to it. I hope you're still awake after lunch. So back to the quantum circuit model or gate model. Before, in the first part of the tutorial, we talked about some of the famous quantum algorithms, like Bell's circuit and quantum teleportation. In this part, I'll give you some of the application of quantum computing in our research area, basically in positioning and navigation. Let's start. So let me give you just a brief introduction about the problem we are trying to solve in location tracking. So if you talk about location tracking, what comes to mind, of course, is the global positioning system, the GPS, and the equivalent system like Baidu, GLONASS, and so on. However, these systems work only outdoors. They don't work indoors because of they require line of sight to the satellites, and the satellite signal doesn't penetrate into buildings. So in order to do indoor localization or positioning, we need an alternative technology that works indoor. One of the famous positioning technologies is fingerprinting. And the idea of fingerprinting is you have 2 phases. An offline phase where you build your training data. You build your fingerprint. I'll talk about what we mean by fingerprint now. And then a tracking phase where you are trying to find the location based on what you constructed in the fingerprints. So the idea is, for example, you can use Wi-Fi signals in order to determine your location. And what I do, I go inside this floor, for example, and go to different locations in the area of interest. So each one of these blue dots represents a data collection location. So I go to this location, stand there for some time with my device, and then I record the signal I'm receiving from each access point in the environment at this particular location. So it's like a wireless fingerprint, a fingerprint of the wireless signal. And I store this in the fingerprint database, and then I move to another location, collect the signals, and so on. So this is a calibration phase that I do once. And after this calibration phase, I have for each one of these locations the signature of the different access points, and this is what we store in the fingerprints. During the online tracking phase, I'm standing at unknown location, but also I have my device and I'm hearing some signals from the access points. And what I'm doing is I compare what I'm currently receiving to what I stored in each one of these blue dots, and I return the location that has the closest similarity in the signal strength space. So this algorithm can give very high accuracy in tracking, and it can work with cellular, with Wi-Fi, and 2D, 3D location. We have a number of papers addressing different locations, but most of our work so far has been using classical algorithms for this matching to compare what I'm currently hearing, what I stored in the calibration fingerprint. The challenge, of course, is this matching process doesn't scale to a worldwide scale. So if I want to do indoor positioning in every building around the world, I need to construct this fingerprint, and I need to match with all these fingerprints in all buildings around the world, which is not scalable. Not scalable in terms of the matching time, and not scalable in terms of the database required to store the information from all these fingerprint locations. So what we thought about is, can we leverage quantum computing to scale up this fingerprint matching process? And as I will show you, yes, we can do this, and you can get exponential saving in space and running time by leveraging quantum computing. The nice thing is that we evaluated our quantum algorithm in 3 real test beds, indoor and outdoor, using Wi-Fi and cellular signals. And the nice thing, all of them are getting results from real quantum computers. They are not simulations. We are getting results from real quantum computers. So it's happening, and it's happening today. Any questions about the problem before we talk about the quantum computing algorithm? Good. So this is the overall system architecture. So what we have is online received signal strengths. This is, I'm standing at unknown location, and I'm getting signals from different access points, but I don't know my location. I'm just hearing signals. So this is what we refer by online received signal strengths. And this represents my fingerprint that I constructed offline. So at each one of these green dots, I store the signal strength signature from the access points in the environment. So what we do, we start with is these information are coming from a classical device. So these are classical floating point number representing, it's like the bars you are seeing in your mobile, the strength of the signal from different access points. So the first thing we do, we need to convert this classical information to quantum state, to qubits, so that we can process them on our quantum computing. And this is what we call the quantum state preparation step. Once we have this, we do the matching process. Our goal is to find the closest match in this fingerprint location, what I'm currently hearing. And for this, we use a quantum version of the classical fingerprint matching technique. One thing to note here is we are applying this to location tracking, but of course, matching in general is a general machine learning functionality. So you can apply this to different problems because it's a common functionality in machine learning. So let's start by talking about the quantum state preparation. So the goal of this state is to convert a classical vector to qubits. So imagine I have an input vector that has 4 different floating point values. You can think about these as the signal strength from the first access point, second access point, and so on. So I'm having a classical vector of 4 floating point numbers, and I want to convert them to qubits. There are different ways of doing this. What we used in this work is what we call amplitude encoding. So the idea here, I have 4 different numbers. I encode them in the probability amplitudes of 2 qubits. Since I have 2 qubits, I can have 4 different probability amplitudes. So actually, you can think about it. This is like the probability of getting 0, 0, 0, 1. And I'm encoding my classical vector into the amplitudes of the 2 qubit vector. Once I do this, I have my data ready as qubits, and I can start running, processing them using a quantum computer. One thing to note here is my input data classical vector contained a size of 4, and I could encode them using 2 qubits. In general, if my input size is n, I can encode them in log n qubits. And actually, this is what gives us exponential saving in space because of the quantum superposition states. Any questions about the state preparation? Good. So the core of our algorithm is the quantum fingerprint matching, and the idea is you have 2 vectors and you want to calculate the similarity between these 2 vectors. So there are different algorithms, of course, different metrics to calculate the similarity. In this piece of work, we are using the cosine similarity, and I'll tell you later why we choose cosine similarity. Yes, please. You mean the complexity of the state preparation? It depends, of course, on, so actually it takes, I don't remember the exact number, this is a good question, but actually there are different ways to speed this up. So one thing, for example, is to use quantum memory, because this is the fingerprint. You don't need to reconstruct it on the fly. So what you can do is just calculate it once and store it in a quantum memory. And then after that, you can read it. So it is a one-time overhead. You don't have to do it in the online algorithm. But yes, this is a good question. Thank you. So back to the matching. I have two vectors, and I need to calculate the similarity between them. And as I said, this is a common functionality. So we have a paper in the IEEE JSAC journal where this is the quantum similarity algorithm, and the complexity of this algorithm is order log mn, where m, so actually, as we'll see later, the classical complexity is m multiplied by n, where m is the number of fingerprint locations, and the n is the number of access points. So using a quantum algorithm, you can be logarithmic in both, which is, of course, an exponential saving in running time. But just for the sake of simplicity, we'll just focus on this part of the circuit, of the algorithm. And actually, this has a complexity of m log n. So it has still exponential in the number of the access points, but it's more complex. You need to add a higher complexity in order to get log in both direction. But just for the simplicity, I'll talk about this part. Good. So what we are trying to do is, if these are my two signal strengths vector, one of them is the online, what I am currently hearing, and the other is one vector, one dot, one green dot. And I want to compare what I'm currently hearing to one location in the fingerprint. And as I said, I want to calculate the similarity, and we'll take cosine similarity as the metric here. And you can show that cosine similarity, if you are working with qubit, it would be the amplitude, the dot product. So actually, this is the Dirac notation. So this is the dot product between the two vectors, because they are normalized, they are unit vector. So actually, this circuit, I claim that this circuit calculates the dot product or the cosine similarity between these two vectors. If you look at it, why does this calculate the cosine similarity? This is what I'm going to explain in the next slide. But actually, the approach is exactly the same approach I showed to you in the quantum teleportation and the Bell's circuit. So the idea is you start from the input, the joint state, and then see how it evolves from one level to the other. So the initial state, of course, of the joint state is 1 psi and phi. This is the initial joint state. The first operation I'm going to do is the Hadamard gate, and this is applied only on the first qubit. So what would be the state after the Hadamard gate? Any guesses? Anyone remembers? It's equal superposition of 0 and 1, and since this is 1, we'll have a negative sign. So it's an equal superposition of 1, and these are not changed because I didn't operate on them. So exactly, so this one will be 0 and 1, and this is negative, and these are repeated just by distribution. The next step is to apply this gate. What is this gate? Anyone remembers? C, it's a C, it's controlled, but controlled what? Exchange, thank you. It's a swap, controlled swap. So how does it work? If the control is 1, it does swapping. If the control is 0, it doesn't swap. So actually here I have two components because of the linearity and superposition property. I can apply to each term and then combine the outputs. So this is 0, it means the gate is disabled, so no swapping. So this will go as is in the output. This is 1, so actually they will be swapped in the output. So this is exactly what happened. This remains the same, and this has been swapped. What is the next step? Is to apply a Hadamard gate again on the first qubit. What will the Hadamard gate do? It will convert this to equal superposition with a plus sign, and this is to an equal superposition with a negative sign. So this is what we do. and this is the state immediately before measurement. Okay? If I measure the first qubit, what will I get? I measure a single qubit. What do I get? It will collapse to a classical bit. So I'll get a classical bit, 0 or 1, with what probability? One-fourth and one-fourth, but they have to add up to 1. But if this is 1/4 and 1/4, which is the square of these, it would be 1/2. So something is not correct. So actually, what is not correct? This is not normalized. I need to re-normalize. Okay? So actually, before I measure, I need to re-normalize. It's actually mathematical manipulation, just to get the correct probability amplitudes. If you do this, actually, this is the same term, but with normalization. Okay? So now it's clear, when I measure, I get 0 with this probability, and I get 1 with this probability. And they have to add up to 1. Okay? Good? And we are done. We are done. What were we supposed to do? To get this mathematical expression? Yes, cosine similarity. So what does this has to do with, we have the cosine similarity here, maybe in the next slide. Yes. What does this has to do with the cosine similarity? Anyone can see it? Exactly. So actually what I'm looking for is this. This is my cosine similarity. And it appears in the probability amplitude. Right? So the idea is, the term I'm looking for here is the probability I will get 0. So how do I estimate this term? I run the circuit multiple times, for example, 1,000 times, and see how many times it got 0. And by this, I get an estimate of probability of 0. And from the probability of 0, I can get an estimate of this. Easy. So actually here, since it's a probabilistic algorithm, I need to repeat it. And then I use statistics in order to estimate the quantity I'm looking for, which is part of the probability of 0. Which is an interesting way of getting it. Of course, the devil in the details, meaning why this is 1, not 0. If it's 0, it wouldn't work, because I benefited from the negative sign. Why is cosine similarity? Actually, if it's another metric like Euclidean distance or whatever, it's a different circuit. It is not straightforward. So it is not that you take your classical algorithm and run it on a quantum computer. You need to think about it in a completely different way. Think about how did Shor came up with his factoring algorithm. It is not that trivial. Great. So as I said, what we do is we repeat this circuit multiple times. We call this repetition the number of shots. How many times you need to repeat your circuit, because this is statistics. You need to run it enough number of shots in order to get reliable estimates. I'll show you some results on the effect of this K. But once you repeat it, this is how you estimate the probability. Another interesting thing, of course, is the probability of 0 and 1. Of getting 0 and 1 is 1 minus the other, because they have to add up to 1. So actually, theoretically, it doesn't make a difference whether I estimated the cosine similarity from the probability of 0 or probability of 1. They are the same. But actually, as we'll see in practice, it makes a difference. And this is because of the noise in my quantum computer. So I'll show you in the next slides. Any questions about the circuit and how it calculates the cosine similarity? Great. Where? This one? So actually these are, it is not just a single qubit. This is a register. For example, when I had 4 access points, I encoded this in 2 qubits. So actually this is not just a simple term. It's a larger register. We call it quantum register, which is a number of qubits. Great questions. So let's look at the theoretical complexity.
Just before that, I have a question.
Sure.
Before we normalize, this equation was wrong, right? So
not wrong. Actually, it's the same thing, but the problem, it is not clear because, as I said, these are vectors or registers. It's not just a single qubit. It's a register. It's mainly mathematical manipulation.
The same circuit. We didn't change anything in the circuit.
It's just mathematical manipulation.
Just material.
Yes. So actually going from here to here, just mathematical manipulation. It's like when you have a vector and you want to normalize it, you divide by the length and multiply by the length. So you divide and multiply by the same quantity. Same thing. Good question. Other questions? Great.
There is a paper about this, right?
Yes, we have actually multiple papers about this, and actually this is related to a question I got in the morning. When we started this, maybe we started 4 or 5 years ago. At that time, we didn't have enough expertise, so for us, it's a very hard topic. So what we did, actually, this is a swap test. We didn't come up with it. It's a known circuit for calculating cosine similarity. What we did is we applied it to our specific application domain. But once we have this, it is not actually trivial to go to the bigger circuit. So actually, the next one is log, as I said, in n only. To make it log mn, it is not straightforward. But as usual, you start with a simple problem and then complicate it when you gain more knowledge and you know more about the problem. So this is the theoretical complexity. As we said, m is the number of fingerprint locations, the number of green dots. And the n is the number of access points. How many access points you can hear at each fingerprint location. So we said classically what you need to do is I need to compare the online vector, what I'm currently hearing, to what is stored in the fingerprint. So these are two vectors, and if you want to calculate the cosine similarity, you just go over element by, think about it like Euclidean similarity. You take element by element, so it's proportional to the length, which is order, the space is order number of fingerprint location. This is the space complexity. For quantum, as we said, I can encode it in log n qubits. So this is exponential saving in space. And they have actually, during matching, this exponential saving in space maps to exponential saving in running time. This is for the simple algorithm. And then you need to multiply this by m, because you need to repeat this for each fingerprint location. As I said, the bigger circuit at the beginning gives you log m in the fingerprint locations also, which is, of course, significant. Any questions? Yes, Mark.
I fully understand this argument, but could you not just say that the number of units your device can observe is of course higher and smaller at the same time?
Good. So actually, the point is this the killer app? No, this is not the killer app. It's just showing the potential gain you can get from quantum computing algorithm in this space. Yes, and actually, and you can do clustering, so you don't need to have fingerprint location on a worldwide scale. But actually, part of our arguments is that we are talking about in the future, you have IoT devices, and all of them are wirelessly connected. So in this case, it's not just your access points. You have everything, your light bulb, your projector, everything is connected, and your number of signal transmitter and receiver increases very fast. I understand, yes.
You have this analytics, you want to compare them. It's enough if you look at a certain location and it's already different enough. You know this. Just thinking about whether this is sort of a sparsity option to extend this work. Or
interesting point. So I'm thinking about it. Is there an extension in the quantum direction? I don't know. Maybe there is something interesting there. But I'm talking about in the classical, you can do a number of things in the classical that, yes, exactly. We did a lot of work in the classical world. So yes, exactly. Great questions. Other questions? Amr.
The space complexity here, you need number of bits to encode, right?
Yes. Storage space.
Like space here is not memory, like that's additional person.
It can be memory because the fingerprint itself, as I said, you need to calculate it once. It is not that in each time you need to do this encoding. You need to encode the online signals that you are currently hearing. But the fingerprint is a calibration thing. You did it once. It's like you're training data.
Yeah, but I mean, this is quantum gate application, right?
Yes.
There's no memory. There's no
There is quantum memory.
There is a quantum memory.
Yes.
But you
And
cannot-
there are research on the quantum memory.
You cannot copy from it. There's no clone.
No, but you can read. It is not copying. You can just,
You can read. Okay.
She's negative. Actually,
We'll have that.
nice.
Good to know. Okay.
The other thing, actually, also in the future, we talked about quantum sensors. We didn't talk about them in details. But you can imagine in the future, data is already coming from quantum sensors. So you don't have to do this state preparation thing. Yes, it's already coming for you. So the complexity here actually is just the complexity of the fingerprint matching. If you add the state preparation, actually it can be worse than this because it takes time. But this is a one time process.
Linear, you say?
What is that?
The state preparation is linear.
I don't remember, so I don't want to, yeah. But it's more than this. Great questions. Other questions? Yes, sure, yeah.
The whole problem with linear is continuous, right? Space is continuous, and the values are continuous. And somehow they can do to a discrete space, right?
Yes.
Can you explain that portion, how you make sure that eventually you get to a discrete but accurate enough model?
So it's a trade-off, meaning, actually this is not related to quantum, this is fingerprinting in general. Yes, exactly. So actually it's a trade-off between the fine-grained, more fine-grained you get your fingerprints, meaning the more locations, the higher your accuracy. And that's why actually this is one of the motivation we talked about. The higher the accuracy, it means you need a lot of fingerprint locations. Currently you cannot do it because of the space constraints and the matching time. But if you have exponential saving, this allows you to have much more dense fingerprints and hopefully higher accuracy. Does this make sense?
But then if you have a discrete space, wouldn't it be like also possible to take whatever n you have and represent it to do some logarithmic representation, like whatever n you have, you represent n with logarithmic number of bits, right? So I'm not saying it's.
So I think what you are saying, you can quantize it, for example, in a certain number of bits, and then you can do the same, get the same saving.
I don't know. I'm asking. Right? I'm asking if that's.
Yeah, but I think if you do quantization, you are losing information. But here what we are doing is, without quantization, it's the same amount of information, but you are storing it in less space. And what is this less space? It is the superposition thing. So one qubit can store 0 and 1 at the same time. Classical bit can store either 0 or 1. So if I have 0 or 1, I can, this is 2, I need 2 bytes, I can store them in 1 qubit. So this is the same amount without losing accuracy or resolution, but keeping in logarithmic space. But you can combine both. You can quantize and map it to the other thing. Interesting actual ideas I'm getting from all of you, which is great. Other questions? Yes, please. Is there? Yes, there are many different types of. If you use a different encoding, this will change your algorithm because the algorithm here assumes that the data is in the amplitudes of the qubits. If it's different, the algorithm will change. So they are correlated. Great questions. Other questions? Yes, sir.
When you have multiple people in the room,
Yes.
then you have different combinations of fingerprints. Like you can have, a person here, another one here, and there.
This is interesting. I think you are referring to the device-free version. So this is device-based, meaning you are tracking your device. So actually, it is affected by people around you, but this is factor it will reduce your accuracy if there is a deviation of fingerprint. There is another branch of location tracking that actually we started, which is device-free localization. I want to track a person without them carrying anything. How? The idea based on their effect on the ambient signals. So we as humans, our presence in the environment affects the ambient signal strengths by using machine learning technique, studying the changes pattern in the changes, I can detect your location. In this case, actually, since I'm not carrying a device, it makes a difference, the combination. If I want to track 2 persons, I need to get all combinations. So actually this makes it more suitable because it grows exponential. And actually it makes it more suitable for this quantum. Actually, it's an interesting direction. I think the algorithm will be the same, but actually the motivation is easier. So thanks for bringing this up. Great. This is what you get from brainstorming with great minds. Other comments or feedback? Thanks, Tony. Great. So actually some practical results. So actually we tested the system in one indoor test bed. This is our university campus. And this is an outdoor area in Alexandria, my hometown. So we have 3 different test beds, 2 of them indoor, 1 outdoor. This is the area. 2 of them, the indoor was using Wi-Fi, the outdoor cellular. The number of access points we have and the needed number of qubits. And this is we use IBM Qiskit to simulate. This is a quantum, general quantum circuit simulator, quantum computer. Of course, this was maybe 3, 4, 5 years ago. The public available without any fees, you had just 5 qubits. Today, I think the public ones, you can have 100 qubits. And again, this grows exponential. It is not linear from 5 to 100. It's 2 to the power of number of qubits. So it tells you how they advance in just 3, 4 years. It's usually grow exponential. And I think the same is for D-Wave. You grow very quickly. It tells you how the field is advancing. So this figure shows the effective number of shots. The number of shots, as I mentioned, is how many times you need to repeat the circuit in order to estimate the probability of 0 or probability of 1. And as expected, of course, as you increase the number of, this is the error, localization error. And as you increase the number of shots, your accuracy becomes better because you have a better estimate of the location tracking. But you can see that it saturates around 4,000 shots. This is the CDF of the location error. So the bottom line is the higher is the better. This one is a random classifier, meaning it returns a random estimate of your location. Here you can, this is the quantum and the classical version. The message from here is the accuracy of the quantum and the classical version is the same, but you have potentially much faster speed if you use the quantum algorithm. Some of interesting, actually we had a separate paper about the practicality of the algorithms. So when we started working on this, the public, IBM provided different public machines. So each one of these is a different quantum computer. And this is the number of qubits. So all of them had 5 qubits, except one, this Melbourne machine, had 15 qubits. So initially when you thought about it, we thought that the 15 qubit will give us the best results, because you need only 5 qubits and you have 15, so it's a powerful machine. So it should give us the best results. But actually, this figure shows the median localization error for the different machines. And actually, you can see that the worst one is the 15 qubit machine, which is counter to what we expected. We got confused. We thought about why this is the case, but actually it turned out when we read the literature is the number of qubits doesn't matter. What matters is the quality of the qubit because of the noise in the different qubits. So actually there is actually official term, which is the effective number of qubits, which is actually the number of qubits taking into account the noise of the qubits, which is here what we draw in red. And you can see actually the one with the maximum number of physical qubits is the least reliable one. And that's why it was reflected on the accuracy. And that's why in most of our work, we use the San Diego machine for the results. Actually, these are statistics that you can get from the real quantum computer about the probability of error. So this is, for example, what is the probability of 0 switching to 1 or 1 switching to 0, which is because of the noise. So you prepare the state 0, but actually there are 2 things. One is the coherence time. Coherence time is I prepare the qubit in a certain state, how long it will remain in this state. Because actually, because of the interaction with the environment and so on, it can lose its state. And this, again, one of the main hurdles of manufacturing quantum computing today is the noise and the coherence time.
What are these machine names? These machines on IBM?
Yes, IBM cloud quantum computers. But again, this was 3, 4, 5 years. I imagine today you have more powerful and more variables. So usually when they come up with their new machine, they make the older version publicly available. Yeah. Great. Other questions? So this is also a figure you can get from the IBM API. So it's a 5-qubit machine. So each circle here represents a qubit. And actually this is the color of the circle represent the amount of single gate error. It's a gate that works on a single qubit. So the color, this is the, so the C naught, sorry. The H is a single gate. And this, the color scale represents the amount of error you can get. And the color of the edge represents 2-qubit gate error, like the C naught gate. So if you perform a C naught operation involving these 2 qubits, this is the error you can get. So actually, this is coming from the real machine, and actually, the simulator, you can simulate also the error in the computation. So it's very useful in this regard. This is also interesting. Remember that we were calculating the cosine similarity from the probability of getting 0. And we said you can calculate it from the probability of getting 0 or 1 because one of them is 1 minus the other. So actually, this is what we tried here is if I calculate it from measuring 0 or calculate it from measuring 1. And actually, you can see the accuracy is different. And this is because the probability of switching from 0 to 1 and 1 to 0 is different. So actually, if you consider the noise in your machine, actually your algorithm should depend on this. You should change your algorithm to compensate for the error, at least in the near term. Great. Any questions? Good. So the next part is not related to general purpose quantum computing. Actually, we are using quantum annealing, D-wave, to solve a problem. So I'm getting you some flavor of one of our real problem and how we applied quantum annealing and D-wave machine to solve it in the next part. But I see questions. No, this is actually the machine. So you have APIs that returns to you this information. So you can get a sense, and actually this is what helped us understand things like this. Why this behavior doesn't make sense. Actually, these numbers are coming also from the API. And you can see the Melbourne has maybe one of the worst errors, or one of the worst errors. So probability of 1 to 0 is the highest among all other machines, for example.
So that error is just because of the construction of the qubit.
It's because of the noise. You don't have control. And actually, as I said, I think one of the main hurdles in quantum computers now is how to handle the errors, the noise, and the coherence time. How long you can prepare, because if you need your algorithm to finish within this coherence time. And actually, the more depths, the more layers, because the complexity of the algorithm is the number of layers. So the more depths you have, the more noise that will affect you. What?
Wait for 1,000 cycles to do this. This is something that's here. That you cannot trust that the machine is to do. And if you put it in theory, actually look at how it's implemented, but that's
So yes, you have a compiler that converts, it takes actually a circuit like what we are drawing or a Python code, and then break it down to primitive gates like Martin was saying, and this algorithm it is not optimal to say, and it introduces a depth. And actually you have topology also. It's like classical computer and parallel computing where you have your processors connected in a certain topology. Here it is your qubits connected in a certain topology. So if you want to do, for example, control knots, assuming this is your topology, and I want to do a C naught, for example, between 2 and 4. Currently, they are not here. So actually, you need to do swap in order to make them near each other and then perform the gate. And all of this adds to the depth and to the processing time and to the noise. So a lot of, and I think this in itself has very interesting research direction, taking into account this noise and the compilation and many things to do here. Great questions and feedback.
Maybe just to add this one.
Yes.
This is pretty huge.
Yes.
Just because many functions that you need if you want to use it. Right? So it's a really complex machine. The thing about you have, when you try to do this, you have 5 hours.
Yeah, but actually we imagine it may be, we don't know, of course, the exact answer, but actually our algorithm just uses 5 of them. So we thought that since you have 15, it's easier to map them to choose the best out of these 15. But at least what we found is
Each of them has so many connections that are really nonsense.
exactly, but actually you can see even from here is the probabilities are significant to compare. It can be all of these together, I think. Yeah, please. No, I just used what I choose myself to have it. Yeah. So that's saying there is a huge space. As I mentioned, we did just this because it was interesting to explain the different practical aspects of it. Initially, when you start, you don't think about this noise and you think everything is perfect. But then when you get something that doesn't make sense, you start thinking about it and why this is the case, and then you discover new things.
Is the coherence time kind of like a distribution, like fixed on the machine?
I don't think it's fixed, but yes, I think it would be a distribution. But you have maybe a minimum bound, maximum bound, and then your algorithm, and it becomes worse if you have different processing and many things. Yeah.
How do you know all if you just kind of like make it too long and it's here? You just remove.
I think you will see it from one thing, you see it from the results. Yeah, please.
Stay on a high level.
Yes. Actually, again, you start simple, and then as you go, you'll find it's huge space for, which is interesting for us because this is what makes it challenging. You have a lot of things to explore here.
Maybe shortly also to connect this again to the cube. E-waves is the same problem, right? You cannot call the cube and others, so they have certain topologies supported, and others not. So also the cube has to be reformulated and recompiled in order to match a certain topology that's actually supported. So
Same in D-Wave.
It's very inherent requirement of using that. The device does something else than you want. What you lose on this transition, you don't know.
But as I mentioned, I think what is interesting is this is a classical problem in other like distributed systems and parallel computing. So can you borrow some of the solutions here? I don't know. Great ideas and the question. I think this is interesting. So for the remaining time, I think we have 15 minutes.
We should have a follow-up brainstorming session sometime. We don't have time to meet it today, but if we take notes of these kind of ideas, so even open questions, we don't have to have any answers now, just to show the segmentation community what is the potential, what can they do with quantum. That would be great to write down this kind of notes. I don't understand the details you're talking about, but if you both of you can take notes of that, that would help me.
Sure. So yeah, just to give you an idea about one of application of quantum annealing of one of our problems, and I believe Ibrahim will talk about other problems in query processing and so on, but this is in optimization in location tracking. We already talked about quantum annealing, tunneling, and superposition. And this is the QUBO formulation. So basically, as we said, it's a quadratic problem. So you have pairwise terms between two different binary variables, and you can also have linear terms, and it's still quadratic. So what is the problem we are trying to solve here is the access point selection. So what do we mean by this? I have in a certain venue like here, I have 100 access points. And by using these 100 access points, I can get a certain location accuracy. So the problem we are trying to solve is, can I select a subset of these access points? And instead of 100, I can use only 10. And I can achieve the same accuracy because we have redundancy. So this is what we are trying to do is access point selection. So this is the entire set of access points. I need to select a subset of them that gives me the same accuracy, but with much lower number of access points. And we formulated this as a cube problem, and we solved it on a D-wave machine. So what is the idea? The idea, of course, is in the formulation. So what is our decision variable here? Our decision variable is for each access point, whether it's selected or not. This is our binary decision variable. And then we need to formalize the objective function. So we said that we have the quadratic term and the linear terms. So for the linear terms, it's basically we have a metric that captures the importance of the access points. So if I have a single access point, how important it is to my accuracy. And this is my linear term. It depends only on this access points. For the quadratic terms, it is the redundancy between two access points. So if I select two access points, how redundant, it's basically the correlation between them. If they are correlated across all locations, I can get rid of one of them. So my quadratic terms are the correlation between access points. We call this the redundancy. And our linear term is the importance of each access points. So what we are showing here is for each access point, what is its importance? And you can see there are a lot of gaps here, meaning there are a lot of access points that are not important. And this importance is defined based on a metric that we defined. What does it mean that an access point is important? Here, this is the quadratic term, which is the redundancy between the access points. The more yellow means it's higher correlation, means these are redundant access points. So the perfect here is to have blue, meaning there is no correlation between the different access points. The perfect here is to have all blue, meaning you don't have empty spaces like this. So this is before doing any access point selection. This is the entire set of access points. We have about 500 or so access points. For the sake of time, this is how we define the importance and redundancy. The redundancy is relatively easy, just the correlation between the two access points. And this is what Ibrahim was describing in the morning, the Q matrix and so on. So actually, these are some results. So actually, this is our objective function. This is the quadratic term, and this is the linear term. And alpha is a hyperparameter that we choose. Basically, is alpha is equal to 0, we are maximizing the importance, minimizing redundancy. Is alpha is equal to 1, we are interested more in the importance of the access points. So actually, if alpha is equal to 1, we will select all access points because we think about importance. If the other way around, we will not select any access points to minimize the redundancy between the access points. Good. So what we are showing here is the effect of the parameter alpha on the accuracy. And you can see that the accuracy is almost the same. And this is the number of selected access points, which is the red curve. So you can see I can significantly reduce the number of access points without sacrificing the accuracy much, which is great. So actually here, for example, I can live with about 60 or 70 access points out of 500, and I can achieve the same accuracy. Muhammad.
Is this similar to the idea of principal component analysis in PCA, which you try to reduce the dimension of
Yes, but actually here I'm doing it with a quantum computing algorithm. So I'll actually show the gain in the accuracy in the next slide. So here it tells you I can significantly reduce the number of access points while not losing much accuracy. But what did I gain by using a quantum computer? So just visually, this is a complete data set. This is the importance. As you can see, we said a lot of white is not good, meaning there are many unimportant access points that I'm still including. This is using simulated annealing. You can still see it's better, but still I have some whites. And this is using quantum annealing, it's much more dense in the same amount of time. So in the same amount of time, I can get a better solution, which is another metric for quantifying the advantage of the quantum annealer. Yes, Maria. So actually here it is the same time. I think maybe in the next slide I'm quantifying this, but at least I'm getting better quality solution. We said what is better is you have less white. So you can see this just visually, this is denser than the classical version of it. And also here you are having about 60 or 70 access points compared to 120 access points. Here, this is the redundancy. Again, more blue is better. So this is a complete data set. You have a lot of yellow. Using simulated annealing, you reduce the amount of yellow. And of course, you have lower number of access points, about 120. Here, you can see just yellow on the diagonal, which is the access point against itself. And almost everything else is blue. And you have much lower number of access points compared to simulated annealing. In terms of the accuracy, this is 3D localization. You can see, okay, you are getting almost, this is all access points. And here you are getting almost the same accuracy using simulated annealing and quantum annealing. But actually, I think this is the main advantage, is the running time. So this is, the blue is the classical access, the running time for the classical access point selection. And the orange is the quantum version. And this is the accuracy. So to get 80% accuracy, for the quantum you need, so the quantum you need this amount of time. For the classical you need this amount of time. And then if you use different accuracies, this is the amount of time. And you can see that is always the case that the quantum has better time to achieve the same accuracy. Questions? Great. Amr.
So basically the quantum advantage here would be better time, same accuracy, better accuracy, same time.
Exactly. Exactly. No, exactly. Great. So this is just two examples. We have, as I said, maybe we have been working in this 4 or 5 years. So we have a number of other papers. If you are interested, you can just Google us or just email me asking for more information. Not sure if I want to go into this, but quickly for the remaining time. We talked about quantum sensing. So actually quantum sensors can leverage again quantum physics phenomena to sense the environment. So actually you can sense the acceleration. Actually, let's say I have it. You have quantum sensors for all these quantities, for magnetic field, electrical rotation, acceleration, temperature, and they can have higher resolution and higher accuracy compared to classical sensors. The problem, of course, is currently they are bulky sensors, but as technology advances, we imagine that they will be miniaturized. So for example, if you have a good accelerator and good rotation sensor, what you can do, I don't need GPS anymore. I can just use dead reckoning in order to estimate the location as a standalone solution without depending on any satellites or anything. But again, as I mentioned, the main issue here is the bulkiness of the sensor. I think it depends on the technology. So I don't know. Actually, I have some slides here, but I'm not an expert. I don't want to talk about physics. I'm not an expert in physics. But actually, we are using them. For example, atomic clocks that are used in satellites are based on the quantum phenomenon. So we are already using them in some applications. But other things, they are bulky and maybe they require, in some cases, very low temperature in order to do this. So for example, this is for what I don't remember.
What's called quantum navigation?
Yes, exactly. So the idea here is you have very high quality sensors, and then you don't need GPS. You can just navigate, and actually GPS doesn't work underwater. So you can in space. So all of these scenarios you can use. everywhere. And the standalone, it doesn't suffer from jamming, all of these problems. Yes. So one very important direction in quantum computing in general is quantum encryption. And as I said, this is based on the no-cloning theory. So actually, quantum computing in general, one main application is scaling up, getting better algorithms in terms of speed. But also they have very important application in encryption because of this no-cloning theory. So this is direction where you can investigate this. Quantum networking, I also have some work in networking and the communication. As we said, if your data now is qubits, not bits, how can I transfer them from one location to another? And since you have no cloning theory, again, you need to use quantum teleportation and so on. And of course, quantum machine learning, which I think is the subject of the next talk. And I hope that we convinced you that quantum computing is an interesting field, it's challenging, and it's happening today. So hopefully next year we have many submissions from you who are already started working in this interesting field. Thank you so much. This is it's an outdated version. We have more papers, but if you're interested, you can follow us. Thank you so much, and I'm open for questions.
Okay, great.